So I'd like to describe for you how force and energy relate to the motion of things in astronomical context. So I got a star and a planet here, and I'd like to get the thing going in a way that's fairly realistic. So the idea is the planet and the star actually orbit their common center of mass, something like this. That's a little fast. Let's go a little bit slower. And you can see that the speed of the star is relatively small, and the speed of the planet is relatively high. Let's look at their velocity vectors as they go around. Let's stop them for a second. I'm going to draw in some approximately reasonable-looking velocity vectors that represent the both the speed of the thing and the direction that it's going. And let's get that going again, so you get the idea. Notice that the velocity vectors change direction as they go. And one of the concepts of Newton's laws of motion is that when velocity changes, it requires a force. So the question is, what force is it that's causing these guys to change their motion? Now, it turns out the dominant force in most astronomical situations is the force of gravity. So the notion is that So the notion is that there's a force on the planet due to the star that points toward the star, and at the same time, there's a force on the star due to the planet that points toward the planet. And Newton claimed that these two forces were going to be equal and opposite. So if I get the thing going again with that in mind, you can see that these forces act toward one another. There's a force on the planet pointing toward the center of its orbit. There is simultaneously a force on the star pointing toward the center of its orbit. And what I'd like to do is to take a few moments to cook up some relationships that we can use to understand how the mass of these guys and the speed with which they orbit one another, the speed with which they orbit their common center of mass, are all related. Let's start by looking at the force. So Newton claimed that there was a force between each mass in the universe attracted every other mass in the universe with a force of attraction called the gravitational force, and it corresponded to a constant times the mass of thing 1 times the mass of thing 2 divided by the distance between the two guys squared. Now the constant g in MKS units is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And it turns out to be a constant of the universe. And so long as you express the mass of the two objects in kilograms and you express the distance between the two ones as in meters, then this whole expression works out to be a force in newtons. So this tells us that the bigger the mass involved, the bigger the force, and the smaller the distance between them, the greater the force. And of course, if they're farther apart or they're lower mass, that affects the force. So this is an interesting relationship that turns out to be very important in order to figure out how to interpret what we see when we see planets or stars or whatever moving around. Now, there's another of Newton's laws, the second law, which says that the net force acting on any single object, so the net force, is the mass of that object times the rate of change of its velocity. That's called the acceleration. Now, the notion here is that, say, if we focus on the planet, there's a force on the planet from the star. The motion of the planet is related to the force that's acting. So let's see how that all works out. Okay, so the notion is we have two relationships that Newton described. One tells us how the motion of objects depends on the forces that are acting on them, and the other tells us how the gravitational force depends on the mass and positions of the various objects. All we have to do is to put those two guys together to see how this thing turns out. So you take the fact that the force on an object, the net force acting on an object, changes its motion, and you tie that together with the fact that the gravitational force depends on the position and the masses of the objects and how far apart they are. And we say that, well, if the only force that's acting is the gravitational force, that means that the mass times the acceleration has to be equal to the gravitational force, which has to do with the masses and their positions. Now, the interesting thing about that is that you'll notice that the mass of the planet actually cancels out. It doesn't matter at all. In a separate slide, a separate video, I'm going to explain how the acceleration comes about, but it turns out it's equal to the velocity squared divided by the distance between the guys. Velocity, of course, is nothing other than the circumference of the orbit divided by the time it takes to go around. And so if you put all that in, let's see, velocity squared, that's 4 pi squared over t squared r squared. You divide that by r, and you set that equal to gm over r squared. You'll notice that what you end up with is r cubed over t squared is equal to g big M divided by 4 pi squared. That's the answer. That is called Kepler's third law. So Kepler didn't envision it this way. Kepler didn't know anything about forces. He didn't know anything about acceleration particularly. I mean, he didn't have any theoretical reason to support his discovery that the period and orbital radius of different objects' orbits were related in this way. He discovered that r cubed divided by t squared was a constant for every planet in the solar system. And if you look at this theory, you'll notice that the mass of the sun is the mass that's left over, and since the mass of the sun is the same for all the planets that orbit the sun, this is clearly the result you'd get, given Newton's ideas. Okay, I want to use that same concept to cook up another important formula. So let's start again with mass times acceleration is equal to the gravitational force. Once again, we're going to notice that the mass of the planet goes away. Well, it cancels, I guess. And the next thing is that the acceleration is v squared over r. Put that guy in, and then what we get is v squared over r is gm over r squared. Now notice you can cancel one r, and you get that the speed of circular orbit is the square root of gm over r. That's for circular orbit. And so if we can get the speed of an object, of a planet, say orbiting a star, we can measure, and we know the distance, r, we can use this relationship to find the mass of the star. Or if we can get the speed of a moon orbiting a planet, and the distance between the moon and the planet, we can use this to calculate the mass of the planet. This is exactly the strategy we're going to apply to find the mass of Jupiter in our second project. Okay, for the last idea that I want to talk about, I'm going to introduce the notion of energy. There are actually two kinds of energy that we're going to care about. One is kinetic energy. That's the energy an object has as a consequence of its motion. And it turns out it's easy to calculate. It's just 1/2 mv squared. So this is a conventional definition that turns out to be useful. Let's put it that way. The other kind of energy is the potential energy. This is the energy that results from the interaction of multiple objects. And if I have a mass near a large, let's say a small mass near a large mass, the potential energy turns out to be negative. It's minus g times the product of the two masses divided by their distance. Now, this is very similar to the force equation that we learned, Newton's universal law of gravitation, a couple of slides ago. And it is, in fact, directly related because it turns out work is the amount of energy it takes to move something under the influence of a force, or it's the energy needed for a force to move something from point A to point B, say. And it turns out, if the force is constant, it's just force times distance. So it has units of force times distance. And you can see that this potential energy looks just like the force equation, but instead of r squared downstairs, it's got an r. And that certainly makes sense from a units point of view. It also turns out to be the correct answer in the case of a force that goes like 1 over r squared. If you take into account the work needed to go from point A to point B, this turns out to be the right relationship. You'll notice that this potential energy goes to 0. It becomes 0 as r becomes large. So that means that when the two objects are very far apart, say a small object and a large object, in the limit that they're very far apart, the potential energy goes to 0. As they get closer together, you'll notice that the potential energy is negative. So in an astronomical context, potential energies are basically always 0 or negative. If there's any potential energy at all, it's going to be negative. So what I want to do is to imagine drawing a graph to show how potential energy and kinetic energy sort of work together in order to enable us to predict what's going to happen. So I'm going to make a graph. Let's scooch these guys down a little bit and get them out of the way. I'm going to make a graph where the potential energy, well, let's just say the energy is horizontal. So we have energy going positive to the right. Let's put the 0 of energy right around here. And then at the surface of, say, a planet or something, the potential energy is going to be some negative value. But as you move above the surface out into space, the potential energy, as you can see, becomes less and less negative because r is getting larger. Remember, r is the distance to the center of the planet. So the potential energy is going to do something like this. And it's going to approach 0 as you get farther and farther away. So this is the height. This distance here is the height, let's say call that y, the distance above the surface. And as y becomes large, the potential energy approaches 0. Now the notion is, this is going to be energy. If you have an object and you give it a good throw, so it has then kinetic energy, right? So the total energy is the potential energy at the surface plus whatever kinetic energy you give it. Let's say you give it this much kinetic energy, so that's Ke. And then it's going to go up. Now the interesting thing is the sum of the kinetic energy and the potential energy, that's the total mechanical energy. Kinetic energy plus potential energy is equal to, let's just call it the energy. Now, as long as you neglect any resistance from the atmosphere, any dissipative force from the atmosphere, the sum of these two guys, the total energy, is going to be constant. So what that means is, as the thing goes up, the kinetic energy is going to drop because the potential energy is becoming more positive, and the potential energy is going to, the sum of the two is going to be the total energy, and so the kinetic energy gets smaller and smaller and smaller until you reach some maximum height, at which point the kinetic energy becomes 0, and the potential energy is equal to the total energy, which is going to be some negative number. Then the thing will stop and turn around and fall back down to the ground. So the potential energy becomes kind of a barrier to greater altitude. If you want to go a little bit higher, you've got to start with more kinetic energy. That'll get you up a little bit higher to here, say, and then you'll turn around and fall back down to the ground, and you can keep going. Let's say we get this much kinetic energy. We'll go all the way up to here, getting quite high, and then falling back to the ground. How much kinetic energy do I need to actually get all the way away? I'd have to go all the way to here, so my kinetic energy will fall and fall and fall, but it will never actually reach 0 because the potential energy goes to 0 at infinity at this point. So this is the amount of kinetic energy I need. This is the kinetic energy I need to escape. That's the idea. So let's write that down. The kinetic energy will be equal to the magnitude of the potential energy, because I have to have as much positive kinetic energy as I have negative potential energy at the surface in order to escape. So what that means is that the kinetic energy at the surface, 1/2 mv squared, has to be equal to the magnitude of the potential energy, gmm over r. And notice the m's cancel in this guy just like they did the other time. And I get that the escape speed, now there's this 2, it's going to make the escape speed turn out to be 2mg over r. Notice that that's about 40% higher than the circular orbit speed that we calculated before. But that's kind of the way that one works out. So finally, let me just summarize what we have. We really came up with 3 ideas. One is that r cubed over t squared was gm over 4 pi squared. This is Kepler's third law, K3L, okay? Then we also found that the speed of circular orbits was equal to the square root of gm over r. We got that from Newton's second law and Newton's universal law of gravitation, right that way, okay? And finally, we got the escape velocity was the square root of 2gm over r. And this was from energy considerations. We looked at potential energy and kinetic energy and deduced that this is the speed you need in order to escape a planet or star in the absence of atmospheric friction, which is a pretty reasonable approximation. So, there you have it.